Hello, everybody. I wanted to give you guys a review for the midterm coming up this Tuesday. Just not so much going over a bunch of problems, but to give you some insight into what to expect and what to concentrate on in preparing for the midterm. So I've created a slide deck that will be posted in week 6 along with this recording. And that slide deck is just a condensed version of all of the slide decks that we've been going over the last 6 weeks or so. Okay, so let's get into it. If you guys have any questions between now and Tuesday, please feel free to send me a message, and I'll get back to you as soon as I can, give you feedback on things that you are wondering about. So for starters, I want to strongly advise you to answer every single question, okay? If you leave a question blank, I can't give you any credit for that. Partial credit is, better than 0 credit for a particular problem. There'll be about 10 or 11 questions, okay? And most of these questions will be problem-solving questions. Some of them might not be problem-solving, particularly if we have questions in dealing with intermolecular forces and how that affects boiling point and stuff like that. That won't be a problem-solving kind of question. But for the ones that are problem-solving, anything you write down can at least give you some type of credit. So keep that in mind as you're budgeting your time with this exam. And again, if something's completely blank, that could mean the difference between an A and a B, or a B and a C. Okay, so please try to address all of the questions, at least to some degree. Okay. This is the list of things that I think are important for you to be familiar with as you're preparing for the exam. We talked about calorimetry. We talked about calculating enthalpy of formation and how you can do that using the change in enthalpy values, and as well as looking at bond energies. We certainly went into intermolecular forces. Be aware of the different types, right? We have hydrogen bonding, London dispersion, ion dipole, dipole-dipole. You'll need to know those, and which ones are the stronger interactions, which ones are the weaker interactions, and how that confers different properties, such as I mentioned, boiling point. We also talked about phase change, right? And did some phase diagrams. I'd be familiar with a phase diagram and how to label it and how to interpret it. If we decrease temperature or increase pressure and you have certain values, what happens to the phase as you make those changes? Lattice structures, right? Know how to calculate atomic radius and density for a basic cube and a body-centered cube and a face-centered cube. Solubility, that's going to get into things like molarity, molality, mole fraction. I don't think there'll be much on Henry's law, but definitely the last colligative properties like boiling point elevation, freezing point depression, Raoult's law, and osmotic pressure focus a significant amount of time looking at how to do those calculations, okay? Notice also there's no Clausius-Clapeyron equation here, so you can probably be okay if you didn't practice that too much. Okay. So, starting from the beginning, be familiar with heat capacity and specific heat capacity. The difference is that heat capacity is equal to heat over the change in temperature, whereas specific heat capacity takes into consideration mass. So it's equal to the heat over mass times the change in temperature. And this was pretty basic, right? So you'll be given, for specific heat, if you had a problem dealing with this, you'd be given, 3 of these 4 parameters, and you'd solve for whatever one is the missing one. We also talked about energy being conserved and how, because energy is conserved, we can say that the change in energy is essentially 0, right? Because it's not changing. It's changing in its form, but the amount of it isn't going anywhere. And so we can say that the change in energy is 0, and that's also equal to the sum of the energy in the system and the surroundings of that system. And if that's the case, we can say that the energy of one substance is equal to the negative energy of another substance. And we had some problems where we were heating up metals. That would be, in this case, Q substance M down here at the bottom. And we were sticking it into water and seeing how it changed the temperature. And that would be Q of substance W. We also said that we could use this same relationship in the context of reactions and solutions. And, considering the reaction to be a part of the system and the solution to be part of the surroundings, again, they must add up to 0. And so Q reaction can equal a negative Q solution. Okay. And if Q is equal to, in this case, specific heat times mass times delta T, then if you have those things, you can set up a problem where the specific heat and the mass and the change in temperature of the reaction is equal to the negative specific heat, mass, and change in temperature of the solution, right? So we can, if Q equals negative Q, we can insert C times mass times delta T in for Q, right? And there were several problems where that was done. And here are the problems we did in the lecture. And, if you guys feel like you want to review some of those problems, I put a lot of problems in here because we already covered them. I'm not going to go over them a second time. I would encourage you to revisit some of the lectures on certain problems that are maybe still a little sticky or itchy for you, okay? But suffice it to say, this is an example here where they're giving us a flask containing a certain amount of water, and they give us the temperature of the water increasing from 20 to 85. So that's delta T. How much heat did the water absorb? And so very basically, we're looking for Q. And we're saying Q equals C times M times delta T. And C, because it's water, is going to be 4.184 joules per gram degree Celsius. And that's how you set up this problem, right? Pretty straightforward. As I said in the last lecture, you will not have to memorize these equations, okay? Now, if I give you C equals Q over m delta t, you'll have to be able to, figure out how to get q by itself and do the algebra. But I'm not going to expect you to memorize any of these equations. They'll be given to you, and what you'll need to do is figure out how to use those equations properly to get the answer that I'm asking for. All right. So here is, again, another question dealing with calorimetry, where we say that, the Q of one substance, in this case, metal, is equal to the negative Q of another substance, this being water, right? And so they're asking for, they give us mass, 360 grams. They give us change in temperature for some of it. And they want us to calculate the initial temperature of the rebar. We have specific heat for this steel, and we know the specific heat of water. And so again, we can plug in the different variables, because we say that if Q equals negative Q, we can say C times M times delta T equals a negative C times M times delta T. All right. And so practice this and see if you get that answer at the bottom. Here's another problem we went over, where they want you to identify the metal based on the information you're given. So they want you to essentially calculate the specific heat. And then once you get that, compare it to the list in this table and find out which one it is. And when you do that, you should get a 0.38 joules per gram degree Celsius, which is right on the money for copper. Here's another problem that we went over, again, dealing with calorimetry. And I've typed up the answer, the way to go about getting the answer, how to set it up. And it's important that you, again, practice these calorimetry problems. Q equals negative Q. It's also important to know whether or not it's exothermic or endothermic, right? If your Q is a negative value, that's going to be exothermic. If your enthalpy is a negative value, which we'll get into next, that is exothermic, right? Exothermic is negative. Endothermic is positive. Keep that in mind. Another Q equals negative Q. And again, the Q is positive for this answer down at the bottom. So that's going to be an endothermic process. So again, if this helps out to redo these problems, revisit these problems, and see if you can get them and compare them to the answers here, then that's what I would recommend you do. Another calorimetry problem. And the problems on the test should be similar to the in wording and phrasing to these problems that you see. Okay, I'm not in the business of trying to trick you guys or catch you off guard. I want you to be prepared. I want you to know what you need to know so that you can, show me that you know it. So that brings us into enthalpy and Hess's law. That's another calorimetry problem. Again, with the answer, so you can figure out how to do it. Some more calorimetry. And then first law of thermodynamics, that the change in the internal energy is equal to heat plus work, okay? And the first law, which it's good to remember because we're going to be getting into the second and third laws of thermodynamics next week. First law is that the internal energy of a system changes due to the heat going in or out, or the work being done or by the system, okay? All of that is interrelated, okay? And that these things are state functions, meaning it doesn't really matter how you get to a certain state. All that matters is where you began and where you end, okay? If you took a longer trajectory or a longer path, I mean, and different trajectories, then it doesn't matter, okay? Other state functions are temperature, pressure, volume, mass. Again, it doesn't matter how you got from 0 to 100 degrees Celsius. All that matters is that that was the change, right? And so what is enthalpy? That's the sum of the system's internal energy when set equal, or the sum of the system's internal energy and the product of the pressure and volume. So we say that enthalpy H is equal to the internal energy, U, plus pressure, P, times volume, V. And you don't really need to know this derivative here. All you need to really know is that you can take that equation and essentially make the change in enthalpy equal to heat at constant pressure. Okay. So the enthalpy change is directly related to the heat. And there are three main things we discussed with enthalpy. One is that enthalpy change is indicative of the amount of heat that is involved in a reaction, as well as the number of moles of the reactants and the products, okay? Remember, when we were calculating enthalpy change, we were looking at the moles of the products minus the moles of the reactants, okay? So the amount is important. Also, the enthalpy change depends on the physical state of the reactants and the products, right? So gases of a particular element or compound are going to have a different enthalpy value than, say, liquids. Okay. And so the example here is liquid water has negative 286 kilojoules, whereas gaseous water has negative 242. So the values depend on the state, the phase of these molecules. Okay. And again, as with heat, negative value is exothermic, positive value is endothermic. Remember that. And so here's a problem with enthalpy, 0.05 moles of hydrochloric acid reacts with 0.05 moles of sodium hydroxide to form 0.05 moles of sodium chloride. And they give you 2.9 kilojoules of heat are produced. And what they want to know is what is the change in enthalpy per mole of acid reacting. Okay. And we went over this in lecture, so I won't drive it home so much again. If you are unfamiliar with how to do this problem, go back to that lecture on enthalpy, and we go over this together. Okay. Again, another problem, enthalpy. This was the one with the gummy bears, and they want you to determine the change in enthalpy for the reaction. And how would you go about doing that? Well, you have grams. You got to convert grams to moles by finding the molecular weight. Now, that's a theme of a lot of different problem solving that we've been doing in this class, right? So when you're given grams, like when we get into the colligative properties, right? You're given grams, you got to find moles. And, once you've got your moles, then, you can go from there to say, well, how many moles are in these gummy bears, how many moles of sucrose is in these gummy bears, and how many moles of potassium chloride, and what's the limiting reagents, And from there, you get a certain amount of kilojoules, 43.7 kilojoules of heat. And you can say, well, we get that per a certain amount of our potassium chlorate. So you would divide 43.7 over your moles of potassium chlorate, and that will, and then that should give you your overall kilojoules of, and that was going to be your delta H. Okay. So sorry if that was kind of a rambling explanation, but we did go over this problem in the lecture, and those videos are all on Canvas, so you can revisit those if you want. Now, there are other ways to find enthalpy, right? You can look up the values, the enthalpy values of the products, and you take the sum of the products and you subtract from them the sum of the reactants, taking into consideration the moles as well, of course, right? And we did some problems like that. And then the third way is to look at bond energies. So you often have to draw the Lewis dot structures to see which bonds are formed in a particular molecule. And then you take the sum of the bonds broken minus the sum of the bonds formed, which is the reverse of the enthalpy values. Okay, so for number 2 here, remember that the enthalpy values are products minus reactants. Okay, so products minus reactants. When you're looking at bond energies, it's essentially the reactants, because those are the bonds that are broken, minus the products. Okay, so remember to keep that in mind when you're using these different methods to determine enthalpy change. Hess's law, we went over kind of briefly. I'm not drinking coffee, I'm drinking tea because it's 9:30, so a little late for coffee. And I'm drinking herbal tea, so no caffeine. Anyway, so we'll be dealing with Hess's law later on in this quarter and even in Chem 103. It's important that you understand the concepts of Hess's law because it'll make it easier later on. And essentially, what Hess's law is that if we have some kind of process or reaction that takes several steps, and in this case, we're looking at the context being enthalpy change, we can add up those changes in each of the steps to get the total overall enthalpy change. Because again, these are state functions, right? It doesn't matter how you get to something. All it matters is what you get to from where you started, right? And so again, if you add reactions, you're going to add their change in energies. Okay. If you reverse a reaction, you go from products to reactants, you're going to reverse the sign of the change in energy. Okay, so if it was a positive, now it's going to be a negative. If you multiply or divide reactions, you do the same thing to their respective delta E's. Okay. And then so here is an example. So we're taking 1/2 nitrogen plus O2 and yielding NO2. And essentially we're going to double that. Okay. We're going to say 2 moles are formed. And so it goes from 1/2 nitrogen to 1 nitrogen, from 1 oxygen to 2 oxygen. And so since everything was doubled, right, or multiplied by 2, we do the same thing to the heat, right? We multiply the heat by 2. So 33.2 becomes 66.4. If we have carbon and oxygen coming together to form CO2, but that is a two-step process, and each step has a different enthalpy change, then if we're adding those steps together, we just simply add the enthalpy. And this is enthalpy of formation under standard conditions. That's what the 298 represents. So standard pressure, standard temperature. If we're saying the first step has a negative 111 kilojoules, it's exothermic, right? It's releasing 111 kilojoules. And then carbon monoxide is the product. Then that carbon monoxide reacts further with another 1/2 mole of oxygen, and that yields an additional negative 238 kilojoules. Then that two-step process is going to yield a total of 394 kilojoules up here, right? We added these steps, so we add the enthalpy to get our final answer. This is an example of if we reverse the reaction, we reverse the sign, right? So hydrogen and chlorine. What happened to my annotation? Why can't I? Where is it? It's missing. Okay, well, sorry about that. I don't know where it went. There it is. Now it's back. Okay. So let's try my spotlight. See if that works. So we have hydrogen gas and chlorine gas, and that forms hydrochloric acid, and that's an exothermic reaction releasing 184.6 kilojoules. Well, if we were to reverse that reaction and take the hydrochloric acid and break it down into hydrogen gas and chlorine gas, then it's going to be the opposite. It's going to be an endothermic reaction at 184.6 kilojoules. Okay. And then this is that second method that I talked about. If we want to find the change in enthalpy, we can look up the standard enthalpy values of the products and the reactants multiplied by their respective moles to get overall change in enthalpy. Okay, so again, if you want to know the change in the enthalpy of a particular reaction, you look up the values in the appendix, right, of the products times their moles, and you subtract that. And if there are multiple ones, then you add them together, right? It's the sum of the products times their respective moles minus the sum of the reactants times their respective moles. Okay. And here's an example problem for you to work on. Again, if you want to, if you're pretty confident with this stuff, then you don't have to. But again, here are the different enthalpy values, and some of them aren't in the appendix. So if you remember, I added them here, which you can then use to, again, multiply by their respective moles, which are the coefficients in the reaction. So again, if there's no coefficient, it's just one, you don't multiply it. But the 3 and the 2, you're going to multiply those by the respective enthalpy values in this table. And then the bond energies, of course, you would have to look at the Lewis dot structure for methane. And we did this one, so I'm not really going to do the whole thing, but you know, if you're doing methane, you have a hydrogen, carbon, hydrogen, another carbon, hydrogen, and another carbon, hydrogen. So 4 CH bonds. You look in the table and you'd say, well, where's CH? Oh, it's right here. 415. So that would be 415 times 4. And you look at I2, that's just a bond between 2 iodine atoms. And you say, well, where is that? Oh, that's here. 150 times 1, because there's just 1, right? And then do the same thing for the products. There would be 3 CH bonds and 1 CI bond, and then 1 HI bond. And again, in this case, you take the bonds broken. So you take the associated bond energies of the reactants minus the bonds formed, the products. So it's the reverse of the previous way, okay, of just going straight to the enthalpy changes. Okay, that brings us to molecular forces. Now, there will be questions involving intermolecular, I think I said molecular forces, intermolecular forces, as well as phase change, okay, on the exam. I can promise you that. So it's important to kind of brush up on these again and keep in mind what's going on. Of course, a covalent bond is going to be much stronger than an intermolecular attraction, right? So the bond between the hydrogen and the chlorine here is 430 kilojoules. That would be required to break that, whereas the attraction between 2 hydrochloric acid molecules is only 17 kilojoules to break. So intermolecular forces are weaker than covalent bonds and ionic bonds. But then from there, we go down from dipole and hydrogen bonds to London dispersion forces. And remember, the dispersion forces are the weakest. Every interaction between 2 molecules is going to have some degree of dispersion forces, because we talked about how at any given point, there's a dipole moment where that electron is, or electrons are going to be imbalanced, giving a partial charge on one side. So even if they're not a polar molecule, or even if there isn't hydrogen bonding, there's going to be some degree of weak polarity happening at any given moment. A dipole is a molecule that has 2 different poles, right? A positive and a negative end. This is going to be due to electronegativity, right? So if you have a molecule that's made up of electronegative atoms that's greater than 0.4, if you were to look at the difference between their electronegativity values, then that's going to be a polar molecule. One atom is going to hog the electron more than the other atom. And so that side is going to have a slightly negative charge. And if we have ion dipole interactions where, we have an ionic compound dissolving in solution and breaking apart those ions, the ionic compound into respective ions, right? Then the positive ion, or the cation, is going to have an attraction with the negative end of, let's say, water, right? Because water's polar. And the negative ion, chlorine, if it's salt, is going to have an intermolecular attraction to the positive end of the water. Okay. And so this is just talking a little bit more about the dipole. Dipole, and remember that boiling points are directly related to things like surface area, okay? So the larger the surface area, the higher the boiling point, and that's because the longer the surface area, the more intermolecular forces are at play. So it's going to take more energy to break those apart, which is what boiling is, right? So if we look at these different molecules, they're all pentane, but they're pentane in different configurations, okay? So a neopentane has a distance that is the shortest, right? And so that is a shorter distance, therefore less intermolecular forces going on between these two molecules. Now, if we have isopentane, that's going to be a little bit longer than the neopentane. And so it's going to have a little bit more intermolecular forces. And so it's going to have a little bit higher boiling point, right? And then N-pentane, where it's just one long line, that has the longest distance. That molecule has the longest distance. And so it has the most potential surface area between these two molecules. And so it's going to take even more energy to boil it. So boiling point is directly related to surface area. Boiling point is also related to hydrogen bonds, okay? So the more hydrogen bonds that a molecule has, the higher the boiling point, okay? Also, typically the larger the molecule, the higher the boiling point, because again, the larger it is, the more intermolecular forces are at play, right? So the more energy it takes to break apart those intermolecular forces. Also, if we look at things like the number of atoms, so again, the size of the molecule, the molecular mass, so the size of the atoms in that molecule, and whether it's polar or not, these are going to directly affect boiling point, okay? And something like hydrochloric acid is going to have a much higher boiling point than a difluorine atom because it's polar, okay? And so it's not just one single molecule, right? It's interacting with a bunch of other hydrochloric acid molecules. And so that polarity is going to allow it to have these dispersion forces, these dipole forces, attracting them together, making it harder to break them up. Then we talked about hydrogen bonds, and that's going to be between a hydrogen atom and these really highly electronegative atoms, which we said were oxygen, nitrogen, and fluorine. Okay, because remember, as you go up the periodic table and left to right, you increase electronegativity. So these guys here are going to be the really high electronegative atoms and are going to really want to hog that single electron in the hydrogen of another molecule. Okay. And so that's going to, so, you know, when looking at the, you know, when predicting right? There's a question that goes into like predict which molecules, will have the highest boiling point, or rank the molecules from highest boiling point to lowest boiling point, not giving me the actual boiling point, but just what you think would be the highest. Take this into consideration. Is it polar, right? Is it a big molecule? Does it have a lot of surface area? Are there hydrogen bonds going on, right? Are there hydroxide groups attached that render it able to hydrogen bond? That kind of a thing is what you want to look for to rank things in terms of their boiling point. So looking at this list here, right? This first one, not going to hydrogen bond, right? So X, there's nothing there. This, however, has an oxygen. Oh, nope. No. Redo, undo. This one can hydrogen bond. This one has a nitrogen that can hydrogen bond. Okay. Water has an oxygen. It can hydrogen bond. Okay. So just be familiar with hydrogen bonding with these intermolecular forces. London dispersion, again, those are the weakest of the weaker interactions between molecules. And it's because of this momentary dipole moment. At any given point in the electron cloud, the electrons may have an imbalance on one side, giving it a partial charge, a momentary charge that will then attract it to another molecule. And this is ranking the strength of the intermolecular forces from dispersion to dipole to hydrogen bond, and then the strongest being ion dipole. And then we went over this problem, what kind of forces are happening between these molecules. And again, if you don't know, then look at the recording of this lecture. Because all of these slides are from the lectures that we've done. That brings us to phase change. Be familiar with these different terms, right? From solid to a liquid is melting, reverse is freezing. From liquid to gas is vaporization, the reverse is condensation. From a solid straight to gas, skipping the liquid is sublimation, and the reverse is deposition. And that's going to be helpful, as we talk about phase change, right? And phase diagrams. And remember that when we go from different phases, right, the temperature plateaus for a period of time because all of the heat is being consumed in that change, okay? Kind of like the reverse, what we did in lab this week, where once you get to the freezing point, right, the temperature stays the same for a while, okay? Because all that energy is going into the change in the arrangement of the molecules involved in that phase change, okay? And we had some problems where we looked at the enthalpy of fusion versus the enthalpy of vaporization. And if it's in the context of water, right, it's 6.01 kilojoules per mole for fusion, or 40.67 kilojoules per mole for vaporization. And then we had phase diagrams, right? Be familiar with phase diagrams and how to interpret them, how to label them, right? So know, for instance, that there's my drawing tool, know that that's the triple point, or, maybe be able to draw this, right? I might have something where you have to label it. I might have somewhere where you just have to draw it. Know that this is the critical point, supercritical fluid, right? What's below? Gas, liquid, solid to the left, right? And those lines and where the triple point has changed to some degree, depending on the substance, but we plot it with pressure over temperature, right? And so if you were, given a value here and a value around here, you would know that the state is a gas. And then if we said, well, what if we kept the pressure constant and lowered the temperature, right? Well, that means we're going this direction. If we lower it to a certain extent, that process is what? Deposition, right? It's going from a gas to a solid, skipping the liquid phase. Okay, so this kind of a thing, right? Determine the state of the water at the following temperature and pressures. Or maybe it'll give you, like I said, a temperature and pressure and say it's moving a certain direction, one staying the same, or they're both changing, but what's the phase change involved in that? Right? So maybe this can help you practice labeling the different parts of a phase diagram. And that brings us into things like lattice structures, right? So like I said, be familiar with calculating atomic radii and densities of basic and or body and face centered cubes. Remember, the unit cell is the smallest unit of a crystal, right? It repeats itself to form the overall crystal, and the way that it repeats itself dictates the shape of that crystal, right? And so be familiar with these different patterns, right? What does a primitive cube look like? What does a body-centered cube look like? What does a face-centered cube look like? Okay, they're different from each other, right? And based on their arrangement, they have a different number of atoms, which you'll need when we calculate the atomic radius, right? And we went into that, right? We said a simple cube is 1 atom, body-centered cube is 2 atoms, and a face-centered cube is 4 atoms. And then we also said how you can relate edge length in terms of radius, right? So if you're given the edge length of a unit cell, how can you take that edge length and translate it into the radius? Because again, that's what they're asking for, right? The atomic radius. And it's going to be different from simple cube to body-centered cube to face-centered cube. And this is the way that you do that, okay? This, again, just kind of a refresher of going into how you determine that a primitive cube or a basic cube is 1 atom. And then how you would use that to then determine the radius and the density if you're given the edge length. And you know what type of unit cell it is, right? If you know that it's a basic, then you can use the edge length relationship to the radius to solve that. And remember, we said that the edge length is just 2r, right? For a simple cube. So if the edge length is 336, then that would be 336 divided by 2 equals r. So it's half of that, it's 168. And then the same problem. This is body-centered. Again, it shows you how we get 2 atoms from this unit cell. face-centered, this goes into how we say that it's 4 atoms involved. And then here's a problem. And so again, if you need practice, you can do your ICA that we had on this, as well as, again, the stuff that we covered in lecture, to go over these and refresh your mind on how to do these, okay? Solutions and solubility. So this is the last part, right? This is the stuff that's the most fresh. This is the stuff we covered in a couple different lectures. So you can better believe this will be on the exam. Know molarity, okay? Know what it is. Know how it's different from molality. Know mole fraction, okay? And again, you can calculate the mole fraction of the solute or the solvent, right? It just depends on what the question's asking for. So this numerator, mole A, that A refers to whatever you're wanting to find, either the mole fraction of the solute or the solvent. The denominator is going to be both solute and solvent moles combined. This is that table that breaks it down, and then jumping into different problems, okay? 10.5% sucrose. Remember that you can just take 10.5 grams over 100 grams arbitrarily to designate that, to get your mass, right? Here, this could be a good one to practice and go over again. You're given certain masses and certain molecules, so you look up their molecular weights, and from that, and based on the amounts that you're given, you can determine the molarity, the molality, the mole fraction, so on and so forth, right? And with water, mils are directly translated to grams, but if the solvent is something that doesn't have a density of 1.00 grams per mil, you'll be given that density, and you can then convert the mils to grams using that density. Okay. Another problem. These are all the mole fraction, molarity, molality calculations that we went over in lecture. So just practice them. Again, practice makes permanent, right? So if you want, you can review the lecture and then try it on your own and see if you get the same answers that we came up with in class. I recommend that you try this before you look at the lecture, and just see how close you are at getting the right answers, and then looking at the lectures to see, to judge, rather than do it the other way. I feel like the hardest part of these word problems is knowing how to take this information and set it up, right? So when you have the exam, that's what you're going to have to do. So take these problems, see if you can set them up by yourself. If you can't, then review the lectures, and then come back later and see if you're setting them up right, if you recall that. Okay, so again, all these are practice problems that we've gone over. Raoult's law is that the partial pressure is equal to the mole fraction times the vapor pressure, okay? And you'll be given certain variables, and you'll be asked to, solve for the missing one. And again, if the solute is non-volatile, meaning it doesn't evaporate at room temperature, it's negligible in its contribution to the vapor pressure, okay? So the vapor pressure is just going to be the solvent. And so we can say the partial pressure of the solution is equal to the mole fraction of the solvent times the vapor pressure of the solvent. Here's practice problem. Here's another practice problem. And that brings us to boiling point elevation. Again, the change in the temperature of the boiling point is equal to Van Hoff's factor times the Kb constant times the molality, or the moles per kilogram of solvent. And so the Van Hoff factor is only important if you are dealing with a solute that dissociates from itself and goes from, for instance, 1 mole to 2 moles or to 3 moles. Okay, that changes the molar concentration of your calculation. So you need to take that into consideration. If it doesn't dissociate, then it's just set equal to 1, and it's basically cancels itself out. And as I mentioned in lecture, I will make sure that that's explicit to you, whether or not you need to use I. Okay. Here are some practice problems that we went over. Again, I recommend you try them out yourself. Freezing point is the same thing. The freezing point depression is the same thing as boiling point elevation, only the Kf is going to be different. And you're going to subtract that delta Tf from its normal freezing point. Whereas with boiling point elevation, you're going to add that delta Tb to its normal boiling point. Okay. Here is where the I becomes important. Again, like I said, if it usually with salts and stuff. So sodium chloride, right? It's going to dissociate into 1 sodium and 1 chlorine, and so that's going to be 2 moles. When we actually measure it out, it's 1.9, but we use 2 as the I. Something like iron chloride is going to be 4, right? 1 iron atom and then 3 chlorines. So that's 4, okay? Freezing point depression, what's this one, that one? So this one, yeah. So this is a problem where they want you to solve for I, calcium chloride. And then it says, how does it compare to the expected value? So the expected value of calcium chloride is not in this table, but we know that, again, it's 1 calcium and 2 chlorines, so it should be expected 3. Now, when you actually calculate it out, it probably won't be 3 exactly. I want to say when we did this, it was like 2.9, okay? But you do that because it gives you the molality already, and it gives you the freezing point of negative 0.27, okay? So you got to look up the Kf for this, but oftentimes if it says aqueous solution, the Kf is going to be, the aqueous means it's in water, okay? So you'll use the Kf of water, which is 1.86, I think. Yeah, Kf of water is 1.86. So remember that, right? When you see an aqueous solution, that means it's this, this calcium dichloride is the solute and its water is the solvent. Right? Calculate the freezing point of 1.7 molal aqueous ethylene glycol. So that one, you're not going to need to look at I. There's no mention of I, so it's not an issue here. Same with this one. And that brings us to osmotic pressure. And again, the osmotic pressure is equal to the molarity times the gas law constant times temperature. And you'll have the gas law constant given to you on the test. You don't need to memorize it. It's 0.08206, okay? or the units. I'll give you all of that stuff. You just need to know how to use it. Okay. And so here's some practice problems that we went over, and that is it, guys. Okay. So I recommend that, again, you go through this slide deck, you come to these problems, and you try and figure them out. And if you are hopelessly lost, then go look at, seek them out in the videos. And if you're still hopefully lost, just practice it again, practice it again, and practice it again. And reach out to me if you need to, send me a message. Okay. I wish you all the best on this. I'm not going to say the best of luck, because it's not luck. It just comes down to work. And so I wish you the best. And I'm confident that you'll all do well. If you practice everything on this slide deck and you know how to do everything on this slide deck, I can guarantee you'll probably get a C-. Okay. No, just kidding. If you guys rock through this slide deck and you get it all, you got an A. Okay. So with that, I'll say good night, and I look forward to seeing you all again. Hopefully sometime next week. Okay. Bye.